In this problem, we're giving the following situation. We've got charged plates, here red, positive, blue, negative, that are parallel plates, large parallel plates, moving to the left with a velocity v. And then the top plate slowly moves down with a velocity u. And as it moves down, it feels a force due to the magnetic field in between the two plates. And so it feels a magnetic force due to moving charge in a field, magnetic field. The request here is to find the total impulse delivered to the top plate as it moves down until it contacts the bottom plate. To do that, we just simply use the definition of the magnetic force. So magnetic force is, let's see, this is integral dq. In this case, I'm going to put a u cross the magnetic field. I know the magnetic field from the previous problem, and so showing up the previous problem, we've got this magnetic field here, so I'm just going to write this down. This magnetic field is mu naught sigma v in the minus x hat direction. And so we just have to do that problem. What is dq for us? Dq is, or what is the integral dq for us? Well, that's actually going to be the upper plate, which has dq is sigma dA, and so for us, that means that the integral dq is going to equal to sigma times a. So we use right-hand rule. We know that u is in the minus direction, so u cross minus x. So u cross minus x. Yeah, u cross minus x is going to give us in the positive y direction, and so that is going to be in the positive y direction. And so now let's just plug in stuff here. So the magnetic force is going to be mu naught sigma squared v times a, that a, and then in the positive y direction. Now to find total impulse, and u. To find total impulse, I need to integrate this over time. And so in that case, we would write that the impulse, I, total, is going to equal to the integral dt of the force. Well, sigma's not changing, v's not changing, a's not changing, mu naught's not changing. U is the only thing in here that matters because it's 0 before we start, it moves, and then it's 0 after we end. And so we're going to integrate u over that distance. And so then I total is going to be everything that we have, mu naught sigma squared v a in the plus y hat direction. And then we have this integral dt of u. But the integral of velocity is just the distance traveled. So this is just delta z. It says the I total is sigma naught, or mu naught sigma squared v a times delta z in the plus y hat direction. Now the final thing is I'm supposed to compare this solution to the total momentum stored in the field. Well, that's what we did in problem 2. So looking down in problem 2, we compare these two, and they match.